Let's have a look at what rate means in chemistry.
So the rate of a reaction can be measured in two ways. Either you can measure how fast you're making something, or you can measure how fast you're using something up. For example, if I was reacting calcium carbonate with an acid, I would end up with carbon dioxide being made. Now I could measure how much carbon dioxide is being made in set amount of time, let's say a minute, or I could say, well, how much time does it take to make 30 cubic centimeters of carbon dioxide? I'm measuring how fast the product is made. Or, alternatively, I could measure how fast is my calcium carbonate actually being used up. I could measure the mass of it at the beginning, and I could measure the mass through the experiment, and I could work out how much of it's being used in a minute, or I could use how long does it take to lose a gram of calcium carbonate into the reaction. So that's how we would describe a rate of reaction. And the equation for that would be the change in the amount of reactant or product divided by time. And so that would equal the rate. And now what do we mean by amount? Amount is specifically the number of particles in moles. But actually, practically, we would maybe measure cubic centimeters, for example, a volume of a gas, or we would measure a mass of a solid. And then that's actually proportional to the number of moles. So it's just as useful to put a volume or a concentration or a mass over the top of the fraction, the change in any of those divided by time, because it really just tells you how much of the substance, the amount in moles, is being used up. So if I took the amount of substance used and plotted that on a graph against time, and I had amount used on my y-axis and time on my x-axis, I could plot a graph of reaction, and we'd start with a lot of our reactant, and we would end up with none left at the end of the reaction, but in theory. And we could plot a line like that, and you'll see that actually we have a gradient there of that line. Now, if we can work out that gradient equals y divided by x, and therefore gradient equals amount used, or the change in the amount, divided by time. So therefore, the gradient equals the reaction rate. Now, if I had a steeper gradient, that's a larger number, and so that would be a faster reaction. And you can see that because this line is steeper, I'm using the same amount up in a shorter period of time. That's a faster reaction. Let's imagine it was the product I was producing. So instead of using something up, I'm measuring how much I'm producing. I start with nothing and I end up with this much. If I did a second reaction, which looked like this, you can see that the red line has a shallower gradient, and therefore it's a slower rate of reaction. And you can check that because you can see that the amount of time it takes to get to the top of the graph is much longer with the second one. So it's a slower rate of reaction. So the gradient on a line on any graph where you've got amount or concentration or mass or volume up the y-axis and time across the bottom is going to be equal to the reaction rate. And the units of the reaction rate are always going to be found by taking the y-axis units and dividing them by the x-axis units. So, for example, you might have centimeters cubed up the side, you might have seconds across the x-axis, and you would end up with centimeters cubed divided by seconds, or centimeters cubed per second, and that would be your unit of your reaction rate. So here's an example here, mass of reactants up the side in grams, time across the bottom. So we're going to measure the gradient of this line, and we're going to say that the reaction rate units are going to be grams divided by minutes, or grams per minute. Okay, so let's start at the easiest point that we can find, which is this one here. Up on the y-axis, that's 45, and then this one down here is 5 at the other end of the experiment. And so we can say, right, if we've used up 45 minus 5, that would be 40 grams we've used up in the experiment from the maximum of the red line to the last value that we have there. And we are going to take 10 minutes to do that. So 40 over 10 gives us 4 grams per minute. And that's what we call an average rate, because you can see the red line, the results that we have, doesn't actually form a straight line. And this is typical with rate graphs. They're usually curved. So your average rate is basically when you're comparing an entire set of time. So we've got 10 minutes here, and over the entire time, our average rate was 4 grams per minute. But you can see that at the start, if we only measure this first minute here, we actually use 5.8 grams in a minute. So that's 5.8 grams per minute. And in the last minute, it's down to 2.2 grams in a minute. So that's 2.2 grams per minute. So there is a change in the reaction rate as the reaction is going along. So average rate shows us the change over a set time, and we can compare, for example, two experiments. We run them for 10 minutes with different conditions, and we can compare those average reaction rates, and we can say, well, this one is higher than that one, and therefore this one is a slower reaction rate than that one. And that's useful. But actually, if we want to know the rate at a specific point, because it changes during the experiment, usually it slows down, but there are a couple of exceptions to that. We have to use something called a tangent in order to calculate the rate at any given point. So let's imagine that I've been asked to calculate the rate of reaction at 4.6 minutes. If I take 4.6 minutes and I put it onto my graph as this little dotted line here, you can see that this is somewhere in the middle of the line, and I want exactly on that point what is the rate. I'm not going to be able to do an average rate here. Okay, I'm going to have to do exactly that point. So we're going to draw a tangent, which is a line which touches the curve but doesn't actually go over it and cross it at any point. And so in theory, there is one point where the tangent touches the red line, and that is where the dashed line at 4.6 minutes is. Now, if I was to plot that on there like this, then the gradient of the blue line is the gradient of the tangent, and the gradient of the tangent is equal to the gradient of the red line at the point where the tangent touches the red line, which is 4.6 minutes. So if I've drawn my tangent on in the correct place at 4.6 minutes, so that's the only 4.6 minutes is the only point touching the red line and the blue line, then the gradient of the blue line is going to be equal to the reaction rate. And we find that that's 41 is my change in y, 41 grams. And then my change in x is going to be 9.8 minutes. And we therefore have 41 divided by 9.8. That gives us 4.18 grams per minute. So just those 4 steps again. We draw a tangent that touches the line at the desired time. We calculate the change in the y-axis and the change in the x-axis, and then we divide the change in y by the change in x to get the gradient of the tangent, which is equal to the gradient of the curve at the point it touches. And that gives us the reaction rate.